at linear approximations, and we're going to be using derivatives to be able to make estimates of values that are otherwise difficult to do without a calculator. For instance, we're going to be looking at trying to find the fifth root of 0.95 and the fifth root of 1.1. If you have a calculator handy, this is really simple to do, but how do you do this process without a calculator? Another question is why you would want to. Part of this is, well, mathematically it's fun. Another answer is that there are other mathematical processes going on here that we want to practice as well, and this helps us practice that. And it helps our understanding of what we're really doing when we talk about finding derivatives. This idea of linearization is that we're going to be using this formula, if you will, and notice it's an approximate value, it's not an equal value, and we're going to take the function evaluated at a number, and we're going to take the derivative of the function evaluated at a number, and then we're going to multiply it by x minus a there. Now this should look like point slope form to you. So we're approximating a particular value using y plus y prime times x minus a there. So what we're really doing there is we're essentially saying we're finding a tangent line, and we're using that tangent line to approximate a value that's really close to the actual curve itself. And there's a graphical process you can look through as you do this idea, and that process for something like this fifth root, we're not looking at the entire function, just the little part that's useful to us here. And we're saying right here is the point of interest. Finding that spot on either side of that point of interest, and we're just going to call that 1 for a second, is a little difficult. But if we do a tangent line right there, really close to 1, that tangent line is really close to the actual value of what we're interested in. So we can use that tangent line, and that linear equation is easier to work with than this fifth root is. So we're going to be using that tangent line to help us with that process. Okay, so the first thing we need to do is we need our equation. We need the value of a, or in this particular case we're going to be using a equal to 0, and we'll explain more about why we're using 0 here in a second. The function is x plus 1. Now the reason why we're using x plus 1 is that that's the curve we have, right? And there are other things that go along with that. If we use x plus 1 and the point that we're interested in is 0.95, then the x value we'd want to use here, all right, x plus 1 needs to be equal to 0.95, which means that x has to be equal to negative 0.05, right? Now, again, we go back and we say, well, why are we using a equal to 0? Well, because that makes the calculations a little simpler to do here, because that puts us really close to what we want to be dealing with. So what I mean by that is we're going to do g of, so our approximation of, well, I don't want to write it that way, make it a little bit clearer in what we're actually doing here. The approximation of the fifth root of 0.95 is going to be found by doing g of a, where a is 0, plus g prime of a, which again is 0, times negative 0.05 plus 0. Right? Now that may not make a whole lot of sense of why we're using 0.95. Well, inside the function there is x plus 1. So in order to get this to be 0.95, we'd have to plug in an x value of negative 0.05 to get 0.95. So to get this number, that is the approximation that we're interested in, we have to use this value of x. And then it becomes a little bit clearer why we're using a equals 0, because a is really close to this value of x that we're plugging in, which means our approximation is going to be fairly close. We want these two values to be close to each other. So we can modify this function to fit so that this value of a and this value of x are reasonably close. That word reasonably is really flexible. But anyway, so we get this. G of 0, we go back to our original function. G of 0 is going to be 0 plus 1, which is 1, and the fifth root of 1 is 1. And then g prime is 0, well, there's my derivative, all right? And we plug in 0 again. 0 plus 1 is still 1, and the fifth root of that, and then taken to the fourth power, is still 1, and that's negative, so it's going to be 1 over that, which is 1 over 1, which is still 1. So we're talking about it being 1 over 1 times 1/5, which is just 1/5. You need to pause and back up and redo that, or maybe you can pause and do that calculation on your own, okay? And then you have this whole piece which I'm going to rewrite inside as a decimal since I already have a fraction here. I'm going to rewrite this section as a decimal. So I'm going to write this as 5 over 100. And don't forget your negative sign there. Now, when we do that, we get some cancellation with the 5s, right? So what you're really talking about here is 1 plus negative 1 over 100, which is, all right, let's write it here, which is 99 over 100, or 0.99. So our approximate here is 0.99. So if we were to do the 5th root of 0.95 on our calculator, the approximate value we would get would be 0.99. If you want to take it 3 places, it would be 0.990. It doesn't really change what we get over here, right? We can do this exact same process for the 5th root of 1.1. But in this case, what is the, and everything else really stays the same because we're going to use this same value of a here. So g of 0 plus g prime of 0, and then plus 0 right there. But we got to fill this piece in. But we're not going to use 1.1. The function is using x plus 1. So how do we get 1.1? By letting x be 0.1. Right? So again, we're using there's a value of 1.1 is what we want. We're going to add 1 to something to get 1.1, which means that we need to add 1 to 0.1. So once again, we get 1 plus that 1/5 again, right? And then this time, 0.1 plus 0 is just 0.1. Again, I'm going to write this as a fraction since I already have a fraction there. So that's 1 over 10, right? So this is 1 plus 1/50th. 1/50 is 0.2. So we're saying that this is 1.2. So an approximation of the 5th root of 1.1 is 1.2. Okay? Not 0.2, 0.2. So this needs to be, I'm off by a decimal place there. There we go. Okay? So what we've done is we found a way to approximate these roots, powers, whatever we want to use with decimals using a fairly simple, straightforward process. Now, many of you are thinking, well, I can use a calculator for this. Yes, you can. You can verify that this is reasonably close using a calculator. But there are other things going on here, namely this idea that, or this reinforcement that, the tangent line is an approximate value for the curve when you're close to a particular value of interest here. In this case, when we're reasonably close to a equal to 0 for these other values. Okay? So I hope this is helpful. Reach out with additional questions and comments if you have any. Otherwise, keep mathing on.